What if everything you thought you knew about the universe was incomplete? What if the stars, the planets, and even the very atoms inside your body were not just passive objects moving through space, but elements in a vast, ongoing computation? Imagine a universe that isn't merely a collection of matter and energy, but a process, a system running on rules that calculate every interaction, every event, every moment in time. Not a simulation in the conventional sense, but the real, underlying mechanism of reality itself. Every collision of particles, every photon traveling through space, every quantum fluctuation could be thought of as a calculation. Some physicists propose that the universe itself behaves like a quantum computer, continuously processing vast amounts of information across 13.8 billion years. And if that is the case, then we are not simply made of matter. We are outputs of this cosmic computation. We are information, taking shape in the physical world. Traditionally, we view the universe as a mechanical system, objects interacting under forces, obeying laws, moving in predictable ways. Drop a stone and it falls. Heat a gas and it expands. Yet beneath the familiar motions, a deeper level of reality may exist, one built entirely on information. In physics, information isn't just an abstract idea. It is measurable, persistent, and fundamental. When a quantum state changes, when a star collapses, or when particles scatter, information is transferred. This makes some scientists argue that information might be more fundamental than matter or energy itself. John Wheeler, a physicist who worked closely with Einstein, captured this idea in 3 words: it from bit. Reality, he suggested, emerges from yes or no questions, bits of information that define the behavior of every particle, every force, and every field. These bits, unlike the binary ones and zeros in your computer, are woven into the very fabric of space and time. The universe isn't storing them on a hard drive, it is living them, running them continuously. Think about how computation works. In a computer, input data is processed by a program to produce an output. In the universe, physical laws act as the program, and particles, fields, and forces are the variables being processed. Every photon hitting your eye carries information, which is translated into electrical signals in your brain. Even your thoughts can be traced back to these informational interactions. And at the smallest scale, well below atoms, space and time might not be smooth and continuous. Instead, they could be granular, discrete, and quantized, like pixels on a screen or frames in a film. This granularity suggests that reality naturally lends itself to digital representation. DNA, for example, is a biological code, a sequence of instructions that builds life. Elementary particles too have quantized properties, like energy and spin. Strip it all down, and the universe appears governed by binary logic, a cosmic code of ones and zeros. If that's true, then the laws of physics are not merely descriptions of reality, they are the source code of the universe itself, and everything we observe is the result of running that code. One remarkable implication of a digital universe is that reality is finite. There's only so much information that can be contained within a given region of space. Push beyond this limit, and you create a black hole. The Bekenstein bound, proposed by Jacob Bekenstein, formalizes this principle. The maximum amount of information is determined by the surface area of a region, not its volume. Black holes are some of the clearest examples of this principle in action. Their surfaces encode the information of everything they consume, much like a hologram storing a 3-dimensional image in 2 dimensions. This is called the holographic principle, and it suggests that even the 3-dimensional universe we experience might be a projection of information encoded elsewhere. Information at the core of reality explains many mysteries: why physical laws are precise, why quantum states collapse in predictable ways, and why the speed of light is a fundamental limit. The universe may not just contain information, it is information, processing itself continuously. Unlike simulation theories, there's no outside observer. The universe isn't running on someone else's computer, it is the computer, and all phenomena are the outputs of its intrinsic computations. Even our thoughts, decisions, and experiences are part of this computation. Neurons interact in ways that carry information, creating consciousness as a high-level emergent process. We are not puppets. We are real in the same sense that planets, stars, and galaxies are real. Each of us is a pattern arising from the underlying computational rules. To understand this fully, we need to grasp what a quantum computer is. Unlike classical computers, which use bits that are either 0 or 1, quantum computers use qubits. A qubit can exist in multiple states simultaneously, a phenomenon called superposition. 10 classical bits can represent one of 1,024 possible values, but 10 qubits can represent all 1,024 simultaneously. Add entanglement to the mix, where the state of one qubit instantly influences another, and the computational power grows exponentially. The universe behaves quantum mechanically at its smallest scales. Particles exist in probability clouds. They entangle, interfere, and collapse according to quantum rules. In essence, the universe is a quantum computer running on its own native principles. When we build quantum computers, we aren't modeling reality. We are creating machines that follow the same fundamental rules as reality itself. This realization is the cornerstone of the theory that the universe is computing its own evolution. Black holes, too, fit into this framework. They might not destroy information, but scramble it at extreme speeds, acting as natural quantum processors. Quantum entanglement could form the scaffolding of spacetime itself, with the structure of space emerging from patterns of entangled information. Quantum error correction, used in computing to protect delicate information, might be mirrored in the universe to preserve consistency even in extreme conditions. If the universe is a quantum computer, everything, space, time, energy, matter, and consciousness, is a product of computation. This section lays the foundation for understanding reality not as a collection of objects obeying laws, but as an ongoing informational process, producing every particle, every galaxy, every mind.
If the universe is a quantum computer, then what we perceive as space and time might not be fundamental at all. Instead, space itself could emerge from networks of quantum information stitched together by entanglement. The more entangled two regions are, the closer they appear in space. Pull the entanglement apart, and the regions drift apart. In this view, information doesn't just live inside space, it creates space. The geometry of reality is a direct consequence of how information is connected. Some physicists are now developing models that explore this idea in detail. Mark van Ramsdonk, a leading researcher in this field, has shown mathematically that the connectivity of spacetime can be derived from the entanglement patterns of quantum degrees of freedom. In other words, spacetime itself might be the result of an enormous, ongoing quantum computation, a cosmic network that organizes itself according to informational rules. What we call gravity or distance could simply be the emergent outcome of how information is distributed across the universe. Mathematical tools like tensor networks allow scientists to simulate these entanglement structures. Multi-scale entanglement renormalization ansatz, or MERA, is one such tool. Using MERA, researchers can construct systems in which the underlying pattern of entanglement produces geometries that resemble curved space. These aren't just simulations. They suggest that geometry itself might be the product of computation. The universe may not be something in which quantum computations occur. It may be quantum computation itself, and spacetime is a byproduct. Another compelling connection comes from quantum error correction. Quantum systems are fragile. Even tiny disturbances can destroy delicate superpositions and entanglement. To make reliable quantum computers, engineers develop error-correcting codes that distribute information across multiple qubits, ensuring that the overall system preserves its state. Astonishingly, similar structures appear in models of spacetime. Certain formulations of the ADS-CFT correspondence, a key theory in modern physics, behave like quantum error-correcting codes. This suggests that the universe might naturally protect its information in the same way we protect qubits in a lab. Every region of space could contain information that isn't localized, but spread across entangled connections. Even near a black hole, where conditions are extreme and particles behave unpredictably, the universe may use a form of cosmic error correction to prevent information loss. This perspective reshapes our understanding of black holes, spacetime, and the flow of information. Far from being destructive voids, black holes could be the most efficient processors in the universe, scrambling and redistributing quantum data while preserving it at a fundamental level. Quantum mechanics, the theory governing the smallest scales of reality, exhibits behaviors that reinforce this picture. Superposition, entanglement, and probabilistic measurement outcomes aren't just mathematical quirks. They are the operational rules of the universe's computation. Every experiment we perform with entangled particles, every interference pattern observed in a double-slit experiment, shows information behaving in ways that defy classical intuition but make perfect sense if the universe is computing itself. The patterns we see in laboratories are small-scale windows into the universal algorithm that governs everything. Consider the laws of physics from this perspective. Gravity, electromagnetism, and nuclear forces might not be separate entities, but layers of processing within a larger computational framework. What we perceive as distinct forces could emerge from the same underlying algorithm, appearing different only because we're observing a portion of the system. The universe might not obey externally imposed rules. Instead, the rules could emerge from the computation itself, stabilizing in the regions where information is most consistent. This raises profound implications. Laws of nature, as we know them, might not be absolute. They could vary under extreme conditions, near black holes, at the edges of observable space, or in the earliest moments after the Big Bang. In a broader, connected quantum system, different regions could run slightly different versions of these rules. Some physicists interpret this as a form of multiverse, not parallel Earths, but segments of a vast informational structure executing different computational variations. Each region would still be part of the same universal process, but the local manifestations of reality could differ based on the underlying computation. Energy, too, can be reinterpreted. Traditionally, energy is the capacity to do work or cause change. But in an informational universe, energy may be more fundamentally tied to information processing. Erasing a bit requires energy. Storing and transmitting information consumes energy. Viewed this way, the Big Bang may not have been the creation of matter and space, as much as a boot-up event, providing the energy necessary to run a universe-scale computation. Thermodynamics then becomes a statement about information flow. Entropy increases not as chaos, but as the system explores more configurations, more informational states. The universe is moving towards states of greater informational richness, and what appears as disorder is simply complexity in the making. In this computational view, complexity itself may naturally emerge. From atoms to stars, molecules to life, consciousness to self-awareness, complex structures arise because the system favors feedback, interaction, and information integration. Complexity isn't a coincidence or a mystical goal. It's a statistical inevitability when information flows through a coherent, rule-governed system over billions of years. Patterns of order, structure, and intelligence appear because they are stable manifestations of ongoing computation, not because the universe intends them. Humans are a remarkable consequence of this process. We are both participants and observers, made of the same informational substrate that creates galaxies and particles. What sets us apart is self-reference, our ability to reflect on the system that produces us. Consciousness allows us to study the universe, understand its rules, and model its computations from within. Science itself can be viewed as a recursive feature of the universe, the system computing its own structure through embedded observers.
Once we start thinking of the universe as a quantum computer, an inevitable question arises: can we simulate it? Could a civilization, given enough knowledge and technology,
build a machine that mirrors the universe itself. At first glance, this seems conceivable. We already create models of galaxies, black holes, and quantum systems. We simulate atoms, molecules, and their interactions using powerful computers. With advances in quantum computing, even small-scale quantum systems can now be simulated accurately. But here's the catch. Simulating a system from within itself is not straightforward. In computer science, no machine can perfectly simulate itself with full precision. This isn't just philosophical, it's a mathematical principle. A system trying to replicate itself exactly would require at least as much memory and processing power as the original. And since it exists inside that original system, it cannot exceed the system's total capacity. This is a reflexive limitation. A mirror cannot reflect itself fully. A book cannot contain an exact copy of itself within its pages. The limits of simulation appear not only in computing theory, but also in physics. Consider the Bekenstein bound, a principle stating that any region of space can only hold a finite amount of information proportional to its surface area. Attempting to simulate the universe in perfect detail would require storing information equal to or exceeding the universe's total capacity, an impossibility from within. Any simulation we create will necessarily be approximate, statistical, or partial. Perfect replication is forbidden by the system's own constraints. Quantum computers offer an intriguing twist. Unlike classical computers, quantum computers don't simulate quantum systems by sequentially calculating each possible outcome. They exploit superposition and entanglement to explore multiple possibilities simultaneously. In a sense, a quantum computer can mirror aspects of quantum behavior much more efficiently than classical machines. But even here, limits persist. Simulating the entire universe with full fidelity would demand a quantum system as vast and complex as the universe itself. There is no shortcut. This limitation leads to a profound insight. The universe may never be fully knowable from within. Any observer or embedded civilization is constrained by the computational capacity of the universe itself. We can model sections, approximate behaviors, and predict trends, but the full picture remains inherently out of reach. It is not ignorance or lack of technology, it is a fundamental feature of reality. The implications of this are staggering. We often assume that physical laws are external constants, absolute and immutable. But if the universe is computing itself, then laws are emergent. They are the stable patterns that persist across long-running computations. What we perceive as fixed rules may be local features of the computation, stable because they produce reliable outcomes in our region of the informational network. In extreme environments, near black holes, in the early universe, or at cosmic boundaries, these laws may differ or behave unpredictably. Even the concept of time can be reconsidered. In classical physics, time flows steadily, independent of events. But in a computational universe, time could be a measure of computational steps, the sequential updates of information. Each quantum interaction, each collapse of a wave function is a tick in the universal algorithm. Past, present, and future may not be distinct in an absolute sense, but are points along a dynamic process of calculation. Entropy and thermodynamics, too, gain new meaning. The second law, that entropy always increases, can be reframed as the universe exploring more and more informational configurations. Disorder, from this perspective, is simply unorganized or unobserved information. Complexity emerges naturally from this flow. Atoms coalesce into molecules, stars form, life emerges, and consciousness arises, not as a miraculous exception, but as an inevitable outcome of ongoing information processing. Human consciousness becomes especially significant in this framework. Our ability to reflect on the universe, to model it, and to discover patterns
is a recursive feature of the computational process. We are subsystems within the universal computation, capable of self-observation. Science, logic, mathematics, and even philosophy may be the universe computing itself, observing its own rules through embedded observers. This raises deeper philosophical questions. If the universe is a quantum computer, is there a purpose to the computation? Perhaps not in a mystical sense, but statistically, the system favors the emergence of complexity. Structures capable of interaction, feedback, and self-organization will naturally arise. Life, intelligence, and consciousness are not accidents. They are natural expressions of information flowing through a consistent computational framework. In this light, our existence is both ordinary and extraordinary. Ordinary because we are just another output of the system, obeying the same rules that govern stars and black holes. Extraordinary because we are rare, processes capable of understanding themselves, of modeling the universal algorithm that produced them. Self-reference, the ability of a system to encode, reflect, and iterate upon itself, may be the most unique and valuable feature of the cosmos. If we consider the universe as a quantum computer, then the Big Bang might not just be a violent explosion of matter and energy. Instead, it could be thought of as a boot-up event, the initialization of a vast computational system. At that moment, the universe gained the energy and structure necessary to begin processing information on an unimaginable scale. Every particle interaction, every force, every quantum fluctuation that followed can be seen as a computational step in a universal algorithm. Energy in this framework is deeply intertwined with information. In classical physics, energy is the capacity to do work, to move objects, to create change. In information theory, energy is the cost of computation. Erasing a bit requires energy. Transmitting a bit consumes energy. Even the processes that maintain stability in a system, from quantum states to macroscopic structures, are part of this computational accounting. The universe isn't just conserving energy, it's balancing the processing of information. This leads to a profound reinterpretation of entropy. Traditionally, the second law of thermodynamics tells us that entropy always increases. Disorder grows. Systems move toward equilibrium. But in a computational universe, entropy can be viewed as the system exploring more and more informational configurations. What appears as disorder is really the universe probing the full space of possibilities. Complexity, far from being exceptional, is a natural result of this exploration. Over billions of years, simple matter gave rise to stars, galaxies, and planetary systems. Chemical reactions formed molecules, some of which organized into the earliest life. Evolution introduced feedback loops and self-organization. Eventually, consciousness emerged, subsystems capable of observing, interpreting, and understanding the computations they themselves were part of. This is not a random occurrence. It is statistically favored in a system that continuously processes information and seeks stable patterns. This brings us to a profound reinterpretation of purpose in the universe. Not purpose in the human or mystical sense, but in the computational sense. The system might not have a predefined goal, yet patterns emerge naturally because the rules governing information flow produce structures capable of interaction and self-reference. Life and intelligence are simply stable outcomes of the universe performing its calculations over time. Our consciousness plays a unique role. While particles, atoms, and stars process information passively, we actively reflect on it. Our minds act as recursive subsystems capable of modeling and testing the rules of the universe. In essence, the universe has produced structures that can compute itself from within, analyzing, iterating, and refining its own algorithmic patterns. Science, mathematics, and philosophy are thus expressions of this recursive computation, embedded within the very system they seek to understand. The universe's computational nature also reframes our understanding of laws of physics. Traditionally, we think of laws as fixed, immutable rules, external. But if the universe is computing itself, laws are emergent properties,
patterns that persist across long-running, stable regions of the computation. What appears universal may only be local stability. Near black holes, in the early universe, or at cosmic boundaries, rules may shift. Different regions might implement slightly different versions of these computational algorithms. This could be thought of as a multiverse of computational rules where distinct regions explore alternative information processing pathways. Even time can be seen differently. Classical physics treats time as a constant backdrop. In a computational universe, time might be the sequence of information updates, the ticks of a universal algorithm. Each quantum interaction, each wave function collapse is a computational step. Past, present, and future are not absolute. They are markers along a dynamic informational process. So what emerges from this view is staggering. We live in a universe that is 1. Finite in information capacity, governed by bounds like the Bekenstein limit. 2. Self-referential, capable of producing observers that understand parts of itself. 3. Complexity-friendly, a system where ordered structures naturally emerge from statistical tendencies. And 4. Computationally driven, where energy, entropy, and laws are expressions of information flow. We often think of reality as solid, composed of particles, forces, and objects. But beneath that, reality may be entirely informational. We are not just matter in motion, we are outputs of a vast quantum computation. Every thought, every feeling, every event is part of this algorithm arising naturally from the flow of information. This perspective doesn't negate daily life. Gravity still pulls, light still shines, and chemical reactions still proceed. But it adds a deeper layer of understanding. Reality is not just happening to us, it is computing itself through us. Our existence, intelligence, and awareness are integral to the system, part of the very fabric of the universal algorithm. The implications are profound. If the universe is fundamentally computational, then exploring, observing, and understanding reality is not just a human endeavor, it is the universe observing itself. Every experiment, every scientific breakthrough, every attempt to grasp the cosmos is a recursive computation, a reflection of the universe's ability to process, store, and interpret information. In this light, life is neither accidental nor purely deterministic. It is an inevitable outcome of information flowing through a structured, stable computational framework. Consciousness is a natural feature of a universe that processes information recursively. And the laws of physics? They are the code of the program, the rules that define how this cosmic computation unfolds layer by layer, step by step.
If the universe is a quantum computer, then it operates under certain intrinsic limits. Unlike classical machines that can be upgraded or expanded, the universe is bound by the rules it set at its boot up. The Bekenstein bound provides a crucial insight here. It states that any finite region of space can only contain a limited amount of information, proportional not to its volume, but to the surface area enclosing it. This means that even as the universe expands, the information capacity of each region remains finite, encoded on its boundary. Black holes exemplify this beautifully. The surface of a black hole, its event horizon, stores the information of everything that has fallen in. Nothing is lost. Everything is scrambled and encoded at the edge. This is the essence of the holographic principle, one of the most revolutionary ideas in modern theoretical physics. What we perceive as three-dimensional space may be a projection of information encoded on distant two-dimensional surfaces. In other words, our reality could be a hologram, a reconstruction of fundamental informational bits projected into the space we experience. This aligns with the concept that the universe is not merely containing information, but is information. Quantum entanglement further supports this idea. Particles separated by vast distances remain connected in ways that defy classical intuition. Entangled states suggest that the structure of spacetime itself could emerge from these informational relationships. The glue of the universe might not be matter or energy, but patterns of entanglement. The geometry of space, the distances, the curvature, the connections, could be a byproduct of how information is distributed and shared across the system. The implications extend beyond physics into the realm of computation and self-reference. In computer science, recursive systems are capable of modeling themselves. Similarly, consciousness can be viewed as the universe reflecting on its own computation. Our thoughts are not external to the process. They are outputs of the same system that governs galaxies and atoms. Through observation and analysis, we participate in the ongoing computation of the universe, interpreting patterns, detecting correlations, and discovering laws. Science becomes a mechanism of self-understanding, a feedback loop through which the cosmos deciphers its own algorithm. Yet, this cosmic computation has limits. A machine cannot fully simulate itself without encountering reflexive constraints. Attempting a perfect one-to-one simulation of the entire universe from within would require at least as much processing power and memory as the universe itself, a physical impossibility. However, partial simulations, approximations, and statistical models are feasible, allowing us to explore and understand vast regions of reality. Quantum computers, in particular, provide a glimpse into how such computations might occur at the universal scale. They leverage superposition and entanglement to explore multiple possibilities simultaneously, mirroring the probabilistic nature of the universe itself. Information flow in the universe also redefines our understanding of cause and effect. Classical physics sees cause as a linear chain of events, but in a computational universe, causality is deeply entwined with information exchange. Each quantum interaction is a step in an ongoing computation, propagating data across the system. What we perceive as randomness, such as a particle's probabilistic outcome in quantum mechanics, may simply be the result of complex information processing at scales beyond our direct observation. The universe as a quantum computer also suggests a statistical bias towards complexity, not in the sense of intentional design, but as a natural consequence of information-rich systems. Patterns emerge, structures stabilize, and self-organizing systems arise. Life, consciousness, and intelligence are not anomalies. They are statistical inevitabilities, products of a system that favors feedback, interaction, and cumulative complexity over time. If we take this seriously, then everything we observe, from the orbit of planets to the rise of civilizations, is an expression of a deeper computation. Particles, fields, forces, spacetime, and energy are all part of the algorithmic substrate. Our experiences, thoughts, and creativity are as much a product of computation as the fusion reactions powering stars. Even time, as we perceive it, is a computational artifact. Each tick, each moment represents the sequential updating of information. Past, present, and future are snapshots of ongoing processing. Events are recorded as changes in information states, building the history of the system step by step. Memory, causality, and observation all emerge from the universe's fundamental informational operations. This perspective also offers a new way to think about entropy and the arrow of time. Entropy is not mere disorder, but the exploration of increasingly complex informational states. The second law of thermodynamics is not just a rule about energy, it is a statement about the universe maximizing the diversity of its computational outcomes. Complexity emerges naturally, and life itself is a byproduct of this inexorable drive towards richer informational structures. If we take this seriously, then everything we observe, from the orbit of planets to the rise of civilizations, is an expression of a deeper computation. Particles, fields, forces, spacetime, and energy are all part of the algorithmic substrate. Our experiences, thoughts, and creativity are as much a product of computation as the fusion reactions powering stars. Even time as we perceive it is a computational artifact. Each tick, each moment, represents the sequential updating of information. Past, present, and future are snapshots of ongoing processing. Events are recorded as changes in information states, building the history of the system step by step. Memory, causality, and observation all emerge from the universe's fundamental informational operations. This perspective also offers a new way to think about entropy and the arrow of time. Entropy is not mere disorder, but the exploration of increasingly complex informational states. The second law of thermodynamics is not just a rule about energy, it is a statement about the universe maximizing the diversity of its computational outcomes. Complexity emerges naturally, and life itself is a byproduct of this inexorable drive towards richer informational structures. By viewing the cosmos as a self-processing system, we begin to see the universe not as a static stage, but as a dynamic computation, continuously updating, evolving, and generating reality. Every particle interaction, every wave function collapse, and every entangled state is a line of code executed on the largest quantum computer imaginable. And in this cosmic computation, we are not mere spectators. we are participants, observers, and outputs of the same process that writes the laws of nature themselves.
If the universe is fundamentally a quantum computer, then consciousness itself may be understood as an emergent property of information processing. Unlike matter, which can be observed and measured directly, consciousness arises from patterns of computation. Our thoughts, emotions, and self-awareness are not separate from the universe. They are the universe interpreting and reflecting upon itself. Just as a quantum system encodes and manipulates information, our brains process vast amounts of data, producing awareness as a higher-level computational phenomenon. This perspective reframes our understanding of life and intelligence. Life is not an accident, and consciousness is not a mysterious anomaly. Instead, both are natural consequences of a universe structured to process information. The organization of atoms into molecules, molecules into cells, and cells into nervous systems is simply one path through which the underlying computation expresses itself. Complexity, self-organization, and adaptive behavior emerge because the computational rules of reality favor stability, feedback, and information retention. Philosophically, this view challenges traditional distinctions between the observer and the observed. We tend to think of consciousness as something that watches the universe from the outside. Yet, in a computational cosmos, the distinction blurs. Observers are embedded within the process, their thoughts and perceptions generated by the same informational flow that governs galaxies, particles, and space-time itself. Our minds are not detached, they are outputs of the universal algorithm capable of reflecting on the process and, in doing so, modifying it in subtle ways. Recursive awareness is particularly intriguing. Humans are among the few systems known to be self-referential, capable of modeling and understanding their own operations. Science, mathematics, and philosophy can be seen as a universe analyzing its own computation. When we discover a law of physics or a mathematical truth, we are essentially reading lines of code written by the universe itself. In this sense, cognition is not merely a biological accident, it is a logical byproduct of information processing reaching a certain level of complexity. This also raises questions about free will and determinism. In a computational universe, our choices are outputs of ongoing processing, yet they are not predetermined in a simplistic sense. Quantum mechanics introduces probabilities, superposition, and entanglement, allowing for genuine uncertainty and emergent novelty. We are participants in a probabilistic computation, and our decisions are part of the unfolding algorithm. Free will may emerge naturally as a property of complex information processing systems capable of modeling themselves and their environment. Moreover, the computational perspective offers a new understanding of time and causality. Time is not a universal flow imposed from outside. It is a sequential updating of information. Past, present, and future are snapshots of states within an ongoing computation. Events occur as data is processed and new outputs are generated, creating the perception of temporal progression. Similarly, causality is not a linear chain, but a network of informational dependencies, where one state influences many possible future states. This framework can also inform our understanding of cosmic evolution. The universe did not evolve randomly. Its history, from the hot, dense early state to the formation of stars, planets, life, and consciousness, is a natural trajectory of a system exploring the full range of computational possibilities. Complexity emerges statistically, not intentionally, because the rules governing information flow favor structures that persist, interact, and replicate. Life, intelligence, and civilization are therefore inevitable consequences of the universe's computational nature, rather than miraculous accidents. The implications extend beyond physics and philosophy into technology and artificial intelligence. If consciousness and complexity are emergent properties of information processing, then creating intelligent systems may be a matter of arranging sufficient computational resources with the right rules and feedback mechanisms. AI may not just mimic human cognition, it may parallel natural processes already operating on a universal scale. By studying the universe as a quantum computer, we gain insight into the principles underlying both natural and artificial intelligence. Ultimately,
The idea of a computational universe transforms our place in reality. We are not passive observers or accidental byproducts. We are active participants in a grand informational process. Every thought, action, and discovery is a reflection of the underlying computation. We are the universe modeling itself, exploring its own possibilities, and iterating upon its own structure. The universe is not a stage, and we are not actors. It is a computation, and we are both the process and its awareness.
If the universe is itself a quantum computer, a natural question arises. Can we simulate it? Could humans, using our machines, build a system that mirrors the universe in full detail? At a first glance, it seems plausible. We already simulate galaxies, atoms, black holes, and weather patterns with impressive accuracy. Our computers model the interactions of particles, gravitational forces, and quantum systems. But simulating the entire universe from within itself introduces fundamental challenges, not technological, but conceptual and physical. In computer science, there's a principle known as reflexive limitation. No system can perfectly simulate itself in full detail without exceeding its own capacity. A book cannot contain a perfect copy of itself on its pages. A mirror cannot fully reflect itself. Similarly, any attempt to recreate the universe in its entirety would require at least as much memory and processing power as the universe itself contains. Since any simulation must exist within the universe, it is constrained by the very limits it seeks to model. There's no outside vantage point from which to perform a complete lossless recreation. This limitation is reflected in physics as well. Consider the Bekenstein bound, which states that a given region of space can only contain a finite amount of information proportional to its surface area. Attempting to simulate the universe fully would demand more information that could possibly be stored within the system itself. Any model would inevitably require simplifications, approximations, or statistical representations. Perfect fidelity is physically impossible. Quantum mechanics adds another layer of complexity. The universe operates on probabilistic rules, superposition, and entanglement. Quantum computers do not simulate quantum systems the same way classical computers do. Instead, they operate within the same rules, exploiting superposition and entanglement to explore multiple states simultaneously. This allows them to efficiently model aspects of reality that classical systems cannot. But even quantum computers face limits when attempting to mirror an entire quantum universe. These constraints suggest a deeper truth. The universe is self-referential. It is a system processing itself from within, unable to fully externalize or duplicate its own complexity. This self-referential property may explain why certain phenomena, like consciousness or the emergence of complexity, appear unique and difficult to replicate. Systems within the universe are inherently limited by the scope of the computation that produces them. Yet, while a perfect simulation is impossible, partial or approximate simulations are feasible. We can model subsystems, galaxies, or even quantum interactions with high precision. These simulations are nested within the larger computation, providing insight into the rules and dynamics governing the universe. In a sense, every experiment, every simulation, every scientific observation is a mini computation embedded within the greater universal process. This view reframes our understanding of knowledge itself. We are not external observers attempting to map an independent reality. We are computational participants studying processes from inside the system that generates them. The accuracy of our models is constrained, not by lack of skill or technology, but by the inherent limits of being parts of a self-contained computational universe. Reflexive constraints also have profound philosophical implications. Concepts like infinity, omniscience, and absolute determinism must be reconsidered. A universe constrained by computational capacity cannot host infinite detail or unlimited predictability. Even the most precise knowledge is probabilistic, statistical, and emergent.
The idea of an ultimate theory of everything becomes not a single formula capturing all of reality, but a framework describing patterns of computation and information flow that generate observable phenomena. Understanding these limits doesn't diminish the universe's complexity, it highlights it. The universe is vast, structured, and computationally rich, but inherently self-contained. We are embedded in a system capable of exploring countless possibilities, yet bound by the fundamental limits of self-simulation. Every particle, wave, and field carries information, participates in processing, and contributes to a computation that is both local and universal, finite and emergent. The universe's reflexive nature also sheds light on the mystery of emergence. Complex phenomena, from galaxies to life, are not externally imposed, but arise naturally as the computation explores available configurations. Constraints force the system to find stable, efficient, and reproducible patterns. Stability isn't luck, it's the computational necessity of operating within finite informational limits. This explains why the laws of physics are so consistent, and why certain structures, such as atoms, stars, and planetary systems, reliably emerge across vast scales.
If the universe is a quantum computer, then black holes are not just cosmic oddities, they're computational powerhouses. They represent extreme environments where information is densely encoded, processed, and scrambled. According to modern physics, when matter falls into a black hole, the information it carries is not destroyed. Instead, it becomes entangled with the black hole's internal states, then released in a highly scrambled form via Hawking radiation. This scrambling is so efficient that black holes may be the fastest information processors in the universe. The idea of holography takes this concept further. Proposed in part by Gerard 't Hooft and Leonard Susskind, the holographic principle suggests that all the information contained within a volume of space can be represented as a projection on its boundary. Imagine a three-dimensional room where every detail is encoded on the two-dimensional walls. In this view, the entire universe could operate like a holographic data structure, where what we perceive as 3D space is actually the emergent result of information encoded at a deeper, more fundamental level. Holography provides a natural bridge between quantum mechanics and gravity. One of the most profound challenges in physics is reconciling these two domains, since quantum mechanics governs the tiny and gravity governs the large. Holographic models show that spacetime itself could emerge from patterns of quantum entanglement. The connectivity of entangled qubits may literally define the geometry of space. If two regions of a system are strongly entangled, they appear close together in emergent spacetime. If disentangled, they drift apart. Space is not the container of information, it is the consequence of how information is entangled. Tensor networks like MERA, multi-scale entanglement renormalization ansatz, provide a mathematical representation of this principle. When physicists use MERA to organize qubits, they find that a curved spacetime-like geometry emerges naturally. This is strong evidence that the structure of space may not be fundamental, but an emergent property of underlying information processes. Quantum error correction adds another layer to the story. In quantum computing, fragile qubits can lose information due to noise or interactions with the environment. Error-correcting codes protect information by distributing it across multiple qubits. Some physicists now suggest that spacetime itself functions as a cosmic error-correcting code, preserving information even under extreme conditions, like near black holes or during quantum fluctuations. The universe is constantly computing, yet never loses information, a necessity for consistency and stability in a quantum computational system. The implications are profound. If space-time and gravity emerge from quantum information processing, then the laws of physics are not pre-existing rules imposed from outside. They are emergent properties of a vast computational network. Forces, particles, and even the arrow of time may simply be manifestations of how the universe processes and preserves information. In other words, physics as we know it is the operating system of a universal computer.
This perspective reframes black holes entirely. Rather than mysterious devourers of matter, they are windows into the universe's computational machinery. The paradoxes that puzzled Hawking, such as the potential loss of information, are resolved when we recognize that black holes encode and process information rather than erase it. The apparent randomness of Hawking radiation is just a result of highly complex computations that the black hole performs on incoming data. Holography and quantum error correction together suggest that the universe is self-organizing, resilient, and computationally efficient. Complex structures arise not by chance, but as inevitable patterns emerging from a system that favors stability, coherence, and information preservation. This principle extends from the smallest qubit to the largest galaxy. The universe is constantly running algorithms that explore possible configurations, discard unstable ones, and encode reliable patterns. In essence, the universe is a self-correcting, self-replicating information processor. The stars, planets, and life itself are the emergent outputs of billions of years of continuous computation. The more we explore quantum mechanics, black holes, and space-time geometry, the more the picture becomes clear. Information is not just a property of the universe, it is the universe.
If the universe is a quantum computer, then the phenomena we observe, from galaxies to human consciousness, are emergent outputs of information processing. One of the most striking features of the universe is complexity. How does order arise from apparent chaos? How do atoms form molecules? Molecules form stars, and stars eventually give rise to life. The answer may lie in the way the universe processes information. In a classical computer, complex patterns emerge naturally when simple rules interact repeatedly. Similarly, the universe's underlying computational processes favor interaction, feedback, and organization. This doesn't require an external designer. Complexity arises statistically as the most probable outcome of long sequences of computation. Over billions of years, the universe has transitioned from a hot, uniform state after the Big Bang to a highly structured cosmos filled with intricate systems. Entropy, the measure of disorder, takes on a new meaning in this context. Traditionally, the second law of thermodynamics states that entropy always increases. In a computational universe, this law can be interpreted as the expansion of possible informational states. The universe is exploring more configurations, generating more patterns, and increasing the information content of reality. What appears as disorder is simply information that has not yet been organized or decoded. Life and consciousness are particularly interesting outcomes. If the universe favors the emergence of complexity, then life is not an accident. It is a statistically favored structure in an information-rich system. Organic molecules interact, self-organize, and reproduce, forming stable configurations that persist over time. Life, in this sense, is a natural byproduct of the universe's computational rules, a recurring pattern that emerges whenever conditions allow. Consciousness takes this a step further. Humans are not just observers of computation, we are participants within it. Our brains are quantum systems themselves, processing information, making decisions, and reflecting on the system that produced them. This is self-reference, a process capable of modeling and understanding itself. In the computational universe, self-reference is rare and profound. It allows the system to iterate on itself, discovering patterns, testing hypotheses, and evolving intelligence. This perspective changes how we think about purpose and causality. The universe is not necessarily striving for a goal, nor is it random chaos. It is exploring all possible informational outcomes, favoring stable, coherent, and complex structures. Life, thought, and civilization are the inevitable patterns in this vast computational process. They are not exceptions, they are natural emergences encoded by the same quantum logic that governs particles and spacetime. The implications extend to our place in the cosmos.
We are not separate from the system. We are a product of it. Our choices, experiences, and innovations are computational outcomes, but with a unique ability: awareness of the computation itself. This self-reflective capacity is rare in the universe and allows us to study the universe's rules from within. In a sense, science is the universe observing and decoding its own algorithm, revealing layers of structure hidden within the fabric of reality. Entropy, information, and complexity intertwine. Stars forge elements, molecules form chemistry, and biological systems emerge. Each step is a computation, a transformation of information into structure. Over billions of years, these processes lead naturally to life and consciousness. Rather than being anomalies, they are expected outcomes of a universe optimized for information flow and stability.
Once we accept the idea that the universe itself is a quantum computer, a natural question arises: can we simulate it? Can we build a machine that mirrors the entire cosmos? At first glance, it seems plausible. We already simulate galaxies, black holes, and even quantum systems to some degree. Yet attempting to simulate a system from within itself reveals profound limitations. One fundamental constraint comes from computer science. No system can perfectly simulate itself with complete detail. This is not philosophical speculation. It is a mathematical fact. A perfect simulation would require as much processing power and memory as the system itself. Since we exist inside the universe, any internal simulation would be limited by the universe's total capacity. Trying to fully encode every particle, every interaction, and every quantum fluctuation would demand resources equal to or greater than the universe itself. This introduces the concept of reflexive limitation, the inherent inability of a system to fully map or replicate itself without loss. A mirror cannot reflect itself entirely. A book cannot contain a flawless copy of its own pages. In physics, this idea appears repeatedly in thermodynamics, in Bekenstein bound, and in quantum mechanics. The Bekenstein bound tells us that any region of space can only store a finite amount of information proportional to its surface area, not its volume. If we tried to simulate the entire universe, we would face the impossible task of fitting a container inside itself. Quantum computers complicate the picture. Unlike classical systems, quantum systems simulate quantum systems more efficiently. Qubits exploit superposition and entanglement, allowing parallel exploration of many states simultaneously. This means we could simulate small quantum systems accurately, preserving crucial behaviors that classical computers cannot. Yet even quantum machines face limits when scaling to the full universe. A one-to-one simulation of every particle and interaction across the cosmos remains physically impossible, not due to lack of ingenuity, but due to fundamental constraints of reality itself. These limitations carry profound implications. First, they redefine our understanding of models and simulations. We can approximate parts of the universe, recreate interactions within bounded systems, and explore probabilistic outcomes. But a complete mirror of reality is beyond reach. Any attempt to simulate the cosmos must simplify, ignore details, or use statistical methods. The universe is too vast, too information-dense, and too reflexive for complete replication. Second, it suggests that our own consciousness and observation are part of the simulation process. We cannot separate ourselves from the universe we attempt to model. Our measurements, our experiments, and even our thoughts are embedded within the computation. This self-referential aspect is unique. The universe does not exist as an external clockwork that we merely observe. It is a computational system that observes and manipulates itself through conscious entities. Finally, this perspective reframes the limits of knowledge. Scientific inquiry, at its core, is the universe modeling its own rules from the inside. Experiments, equations, and observations are reflexive computations performed by subsystems capable of reflecting on the whole.
The impossibility of perfect simulation is not a flaw, but a natural consequence of being part of the computational process itself. If the universe is a quantum computer, we are not external spectators. We are participants, observers, and processors. Every measurement we make, every calculation we perform is part of the ongoing computation. We contribute to the emergent patterns, refine the system's behavior, and uncover layers of structure from within. This makes our role uniquely significant. We are both outputs and analysts, embedded inside the very algorithm we seek to understand. One of the most intriguing pieces of evidence that the universe operates like a quantum computer comes from quantum entanglement. Entanglement is a phenomenon so strange that Einstein called it spooky action at a distance. Two particles can become linked so that the state of one instantaneously affects the state of the other, no matter how far apart they are. This isn't just an odd quirk of physics. It hints at something far deeper. The very fabric of spacetime might be built from information. Researchers have proposed that spacetime is emergent, meaning it is not fundamental but arises from patterns of entanglement. Mark van Romstonk, a leading physicist in this field, has explored how spacetime connectivity could emerge from quantum entanglement. In his work, he shows that entangled quantum bits effectively stitch spacetime together. The more entangled the bits are, the closer they appear to one another in space. Break the entanglement and regions of space separate. This suggests that information is not contained within space, it creates space itself. Mathematical frameworks like tensor networks help make this tangible. Using methods like MERA, a multi-scale entanglement renormalization ansat, physicists can construct geometries that resemble curved spacetime. In these models, entanglement patterns do not merely encode information, they generate the structure of the universe. Spacetime is no longer the stage on which physics plays out, it is the product of computation itself. Another connection comes from quantum error correction. In computing, error correction preserves delicate quantum information. Qubits are easily disturbed, but by distributing information across multiple qubits, quantum computers can protect it. Remarkably, similar mechanisms appear to exist in nature. Certain models suggest that the universe itself might encode information redundantly, protecting it from corruption. Even near extreme environments like black holes, information may be preserved through cosmic-scale error correction codes, hinting that space-time geometry itself could function as a quantum error-correcting system. The holographic principle further supports this perspective. Black holes, despite being three-dimensional, appear to store all their information on a two-dimensional surface, their event horizon. This principle implies that the universe itself could be a kind of hologram, where the three-dimensional world we perceive is a projection of information stored elsewhere. Space and matter are emergent phenomena, while information is a fundamental reality. These ideas collectively suggest that the universe's behavior, from the collapse of quantum states to the formation of galaxies, may reflect underlying computational processes. The strange rules of quantum mechanics, superposition, entanglement, and measurement are not anomalies. They are the logic gates of a cosmic quantum computer, operating on a scale far beyond any technology humans can currently build. In this view, the universe is self-processing, continuously updating and evolving. It doesn't need an external observer to run its computations. Every particle interaction, every quantum fluctuation contributes to the ongoing emergence of space-time, matter, and energy. It's a system that calculates itself into being, with the laws of physics as the program and reality as the output. Understanding the universe in this way challenges every classical notion we have. Gravity, electromagnetism, and quantum fields are not separate entities acting on objects. They are information processes, layers of computation that collectively generate the reality we inhabit. Black holes, far from being destructive, become powerful processors, scrambling and distributing information across the cosmic network. Entangled particles link distant regions, building the connective tissue of spacetime. And quantum error correction ensures that the system remains coherent even in the face of immense complexity and randomness. Ultimately, the holographic and computational perspectives converge to a radical conclusion. The universe is information, and information is reality. This view not only reshapes physics, but also changes how we understand ourselves. Conscious beings, capable of reflection and measurement, are not outside observers. They are participants in the computation, embedded within the same logic that generates everything else.
If the universe is fundamentally a quantum computer, then complexity and consciousness emerge naturally from its ongoing computations. Over billions of years, the universe has evolved from a hot, uniform state to one filled with staggering complexity. Atoms, molecules, stars, galaxies, planets, life, and ultimately, conscious beings. This progression isn't random. It reflects the natural flow of information through a system governed by consistent rules. Entropy, the measure of disorder in classical thermodynamics, gains a new perspective here. Traditionally, entropy increases over time, implying that systems move toward chaos. But in an informational universe, increasing entropy can be seen as exploring more configurations of information. The universe isn't just getting messier, it is processing more possibilities, expanding its computational state space. What looks like disorder is actually information waiting to be structured. In this framework, life and consciousness are not anomalies. They are inevitable emergent properties. The universe's information processing favors structures that interact, feed back on themselves, and self-organize. Complex patterns arise reliably when systems follow simple rules over countless iterations. Atoms form molecules, molecules form cells, cells form life, and life eventually gives rise to thinking, self-aware beings. Consciousness is just another output of computation, a recursive layer capable of reflecting on the system that generated it. This self-reflective property is extraordinary. Very few known structures in the universe can model themselves. Humans can observe the cosmos, formulate scientific theories, and understand the rules that govern the computations producing reality. Science itself becomes a mechanism through which the universe studies its own code, revealing the underlying patterns and logic embedded within the cosmic computation. This perspective reframes our place in the universe. We are not external observers. We are participants, made of the same informational processes that generate gravity, magnetism, and the behavior of subatomic particles. Our thoughts, experiences, and creativity are as real and fundamental as the orbits of planets or the fusion in stars. Consciousness may be rare, but it is simply a specialized output of a highly complex computational process. Furthermore, this view introduces profound questions. If the universe is a quantum computer, what is it computing toward? Not in a mystical sense, but scientifically. Is the system biased toward complexity? Perhaps not intentionally, but through sheer statistical inevitability, complex structures arise. Systems that process information over long timescales tend to explore a wide range of possibilities, giving rise to patterns, self-organization, and emergent behavior. Intelligence and life are part of this statistical tendency, not accidents, but natural consequences of informational dynamics. If this is true, then the universe has its own kind of memory and learning. Each interaction, from particle collisions to ecological systems, contributes to the unfolding computation. Our discoveries, our technologies, and our understanding are extensions of the universe processing information through conscious intermediaries. The cosmos is, in a sense, iterating on itself, with human minds acting as nodes capable of reflecting and refining the ongoing computation. Thinking in these terms also alters our understanding of time. Instead of a smooth, continuous flow, time may be seen as steps in a computation, discrete ticks advancing the universe's informational state. The past is encoded in informational patterns. The present is computation in progress, and the future is the unfolding of possible outcomes determined by existing rules. Reality is both deterministic and probabilistic, governed by quantum logic rather than classical certainty. Finally, this model challenges the boundary between physical and mental phenomena. Thoughts, emotions, and decisions are not mere byproducts of matter. They are information processed in a conscious subsystem of the universe's quantum computation.
Our awareness allows the system to observe itself, a phenomenon unique to entities capable of self-reference. This recursive loop, universe computing, conscious beings reflecting, and the universe observing its own computations, creates a cosmic feedback system where reality and consciousness are inseparable outputs of the same fundamental process.
If the universe is a quantum computer, a natural question arises. Can we simulate it ourselves? Humans already simulate portions of reality, galaxies, atoms, weather patterns, but a full, one-to-one simulation of the universe is far more complex than we usually imagine. The challenge isn't just technical, it's fundamental. In computer science, there's a principle that no system can fully simulate itself with perfect detail. This is called a reflexive limitation. A mirror cannot reflect itself. A book cannot contain a perfect copy of itself within its own pages. Similarly, a universe cannot simulate itself from within without encountering insurmountable constraints. Every particle, every interaction, every fluctuation contains information that must be stored and processed. But the storage medium, the universe itself, is finite. The Bekenstein bound formalizes this idea. It states that any region of space can only contain a finite amount of information proportional to its surface area, not its volume. Attempting to simulate the entire universe would require more information than the universe can physically contain. Even the most advanced quantum computer we might build would be unable to fully mirror reality down to every particle and interaction. This limitation doesn't make simulation impossible, it just forces us to approximate. We can simulate sections, use statistical models, or apply simplifications to understand broader behavior. Classical computers struggle with this because they rely on discrete bits, which cannot naturally represent the probabilistic, entangled states found in quantum systems. Quantum computers, however, are different. Quantum computers work with qubits, which can exist in superpositions of multiple states simultaneously. They can process vastly more information in parallel than classical machines. In theory, this allows quantum computers to simulate quantum systems more accurately, capturing probabilities, entanglement, and interference in ways classical computers cannot. But even with quantum advantage, there remain fundamental constraints. A simulation will always be partial, approximated, or statistical, never a complete duplication of reality. These limits reveal something deeper about the universe. Self-referential systems cannot fully understand themselves in exact detail. Conscious beings, for example, cannot perceive the entirety of their own mental processes with perfect clarity. Similarly, the universe cannot contain a complete, precise replica of itself within itself. Any attempt at internal simulation encounters physical and informational boundaries, just as mirrors cannot contain perfect reflections of themselves. Yet these limitations are not discouraging. They highlight the richness of computation. Even partial simulations provide insights into emergent behavior, complexity, and the unfolding of probabilistic rules. They reveal patterns, correlations, and structures that hint at the underlying algorithm of reality. Studying these simulations is like peeking into the universe's source code without ever opening the full file. Understanding these limits also reframes how we approach science. Experiments, models, and calculations are methods of approximation, ways to probe the rules of the quantum computation underlying reality. No model is ever complete, but each one contributes to a more detailed map of how information flows, interacts, and produces emergent phenomena. The universe is therefore both limitless in its computational scope and bounded by the physical constraints of information. Black holes, entanglement, and quantum uncertainty are not mere curiosities, they are structural features of a system operating at the edge of what is computable. They define the frontier where simulations, observations, and understanding meet the inherent constraints of reality itself. In this light, the pursuit of knowledge becomes a form of participatory computation. Scientists, engineers, and thinkers are nodes in the universal quantum computation, attempting to simulate, observe, and understand the processes that produce reality. Every calculation, every model,
Every experiment is a small step in the larger computational unfolding of the cosmos.
So, what does it mean if the universe is a quantum computer? It means reality itself is not a backdrop against which events unfold. We are not just observers, we are participants in the computation. Every thought, every choice, every interaction is part of the ongoing processing of information that has been running for 13.8 billion years. Our lives, our consciousness, the very structure of space and time are emergent outputs of quantum computations. The laws of physics are not arbitrary, they are the internal logic of this immense system. Gravity, electromagnetism, and quantum mechanics are not separate pieces of machinery. They are layers of processing in the cosmic algorithm. Even phenomena that seem mysterious, black holes, quantum entanglement, and the rise of complexity, start to make sense when seen through this lens. Black holes scramble and preserve information. Entanglement connects the very fabric of spacetime. And the universe naturally tends toward complexity because of the way information is processed. Life, intelligence, and self-awareness are inevitable outcomes of this computational structure, not accidents. And yet, this perspective is humbling. The universe is vast, finite in information, and bound by limits we are only beginning to understand. No simulation can fully capture it. No mind can completely model itself. But in embracing these limits, we gain insight into the elegance, efficiency, and depth of reality. In a way, understanding the universe as a quantum computer transforms our relationship with existence. We are both the computation and the witness, exploring the system from the inside, learning its rules as we evolve. Our science, our curiosity, our technology, everything becomes a form of self-reflection by the universe. So, the next time you look at the stars, or ponder the nature of time, or marvel at consciousness, remember, you are part of the computation. Your thoughts, your creativity, your understanding, they are all expressions of the universe processing itself. And while we may never fully simulate the universe or grasp every detail, the journey of discovery is itself a testament to the power of quantum computation. Every calculation we perform, every experiment we conduct, every model we create is a step deeper into the algorithm that makes reality possible. If this theory resonates with you, imagine the possibilities. What new insights could we unlock if we embrace the universe as information, computation, and connectivity? What new technologies, understandings, or even ways of living could emerge when we see reality not as matter alone, but as a grand, evolving computation of information? Before we wrap up, don't forget to like, subscribe, and hit the notification bell if you want to explore more mind-bending ideas about the universe. Share your thoughts in the comments. Do you think the universe is a quantum computer, or is this just a compelling metaphor? Either way, the journey of exploring it is only beginning, and the adventure is limitless. Because in the end, understanding the universe isn't just about science. It's about seeing the hidden computation behind everything we are, everything we know, and everything we have yet to discover. And that, in itself, is a profound revelation.